Excellent. So yes, I'm Ben. I'm a first year PhD student here at Oxford. So that is called a DPhil here, but equivalently just a PhD. So I'm in the mathematics department, but within that, I'm in the mathematical biology group. So that means that what we do largely as a group is we get data from labs, from clinical settings. We use that data and we aim to make models, mathematical models, to try and predict what they say. And hopefully that can tell us a bit more about the biology that's lying underneath. Um, Within that, obviously, you guys will know, so Oxford is a collegiate system, so everyone gets put into a college. I'm part of Jesus College here, which is a lovely community. Obviously, I've just joined. But yeah, it's been really lovely there so far. We can obviously talk a little bit more about that if you guys want to at the end. But before this, I was doing my master's in maths at the University of Nottingham. So I finished school in 2020, went into my undergraduate degree at Nottingham and studied maths there. So again, very open discussing life at Nottingham there too. Cool. Okay. So there's this quote by George Box that says all models are wrong, but some are useful. So models in this context, we're talking about mathematical models where you use some equation, and it's aiming to explain some truth about the world. So um, something that you could think about is maybe in like GCSEs, A levels, you've looked at like Suvat equations, thinking about how like projectiles would fly through the air. And every time if you plug in, you start with this velocity, this position, you'll end up with the same final trajectory, right? We know that this isn't true. Like if you throw a ball, it's probably not going to land in the same place every time. There's going to be some kind of error in there. But that doesn't mean that that equation, that Suvat equation that you've been studying in school, is wrong or it's not useful per se. So yes, it's not always correct, but it is still useful. And this is something that as you continue with maths modeling, you come to realize more and more that the equations you write down are actually more flexible than you realize. And we're trying to understand the truth that's going on deeper than that. So let's kind of discuss a little bit more what is a model. So it's a description of the real world using mathematical, I've said concepts and language. It doesn't have to be equations. I definitely am an equations mathematician, but not all of them are. If you deal with problems in like topology, say very pure maths, it's described in a very different way. Yeah, first of all, we're trying to provide, some solution to a real world problem. At least that's what I find very motivating. So at least with my work in biology problems, there's so much healthcare that we can delve into. And it's not well understood, and hopefully we can aim to provide insights into that using maths. But it's not obviously just medicine. Obviously, I've said engineering, physics, finance, modeling. All of these are problems that can be helped with mathematical modeling. So let's talk about some ODEs. So hopefully you guys should be familiar with some of these. First of all, let's just kind of go back to what we're talking about by talking about an ordinary differential equation here. So let's talk about these terms, right? So on the left here, dx by dt. Here, x is we're in a biological context, we're going to talk about some like amount of a species, say, some number of animals or people or cells or something like that. And the dx by dt term here is talking about the rate of change of that species over time. Cool. And then on the right-hand side of this equation is the amount it's growing. This on the right-hand side here, kx is saying that the growth of this species is proportional to the amount that's already there. And some of you guys will probably be familiar with this type of equation. If anyone wants to put in the chat how we're going to solve this, what type of equation are we going to try and look for, please feel free. We'll see. Hopefully someone's feeling confident. Okay, so this type of equation here is going to be showing exponential growth, okay, which is used obviously quite commonly in just like a turn of phrase, but mathematically it means something very rigorous, right? It's defined by this, that the growth is proportional to the amount that's already there. So let's discuss it a bit more. So we can use some standard techniques that maybe you guys have started to learn in school, in A levels. Here, we're using this separation of variables technique here. We can go through, we can solve this, and keep going. We can get a nice closed solution of x here over time. So something else we need to include is some initial condition. How many did we start with? I think here we say that at time 0, there's x0 amount of species. Yeah, perfect. And we get this nice exponential growth term here. So what does this mean? I mean, hopefully you guys should be quite familiar with this, in that we're just going to get this really rapid increase over time. This parameter k that we've included here is some growth rate, and that will, by changing that growth rate, we can change how quickly this is going to exponentially increase. And this is something that you can play around with. If you have something like Desmos, you can play around with changing variables very quickly. And that's a good tool to look at, right? If you want to kind of get into the nitty-gritty of things, have a look, try play around with some of these parameters, see what happens. Here, k is 0.1, but if k was 10 times bigger, 10 times smaller, what would we expect to happen? These are all good questions to be asking and something that is helpful in modeling. So going back to the context before, so how is this used? Well, we get this type of problem quite a lot in like cell growth, say, where we assume that the number of cells maybe after every time after a set number of hours, say, every 6 hours, our cells are going to double. And then after another 6, they're going to double again. And then another 6, they're going to double again. And this is like a key result showing exponential growth here. But things aren't that easy, right? We know that if this has been going on since the dawn of time, there would be like uncountably large amounts of cells, which obviously isn't the case. So what's gone wrong? Well, we need to improve our model. Okay, let's talk about some logistic growth. So this here is an equation that we might not have seen before. You might have, but it's a slightly trickier differential equation. Now, have a look at the terms and see what you can think might have changed. It looks kind of similar to what we had before, with this dx dt equals kx, but we've added this extra term in. Okay, any ideas of how we think this might change? Let me stop sharing. Let's see if we can, as n increases, the rate of growth will decrease. Yes. Yeah. That's a great way to put it. So you can think of this in kind of 2 ways, right? You can go ahead and try and solve this equation, which is actually quite tricky to do. You have to include, it should be A-level techniques, that's fine. Or we can think about it in some different ways. So let me stop sharing just quickly and see if we can get this big, if you guys can see the board. I feel like there's a bit of a glare going on. I'm not sure if you can see that very clearly. It might not be a great view to look at it, but we'll give it a go. Okay. So you can go ahead and solve this using like a separation of variables technique that we used before, where you would divide by these x terms over here. like this, and you have to solve. Now this here, this integral we have is quite tricky. You're going to have to use a partial fractions technique, which I'm not sure if we have time for, but you can give it a go. I mean, the solution will be given later. But you can see this is getting kind of trickier already. And if this term was even harder to solve, it would be, yeah, the equations become increasingly difficult to try and solve analytically. But you can think about, what if this growth rate is 0? If dx dt is 0, then that means no growth is happening at all. The number of our species is staying constant over time. So plugging that in, we get kx is 1 minus x over n. And that's equal to 0. Solving this, we can divide by k. That stays the same. So we get two solutions. X is equal to 0, or 1 minus x over n is equal to 0. This here gives us two solutions. Either x is equal to 0, or x equal to n. We've decided, we can decide on what these parameters are, but what we're saying is either if we have our number of cells, x, over time, we've got 0 here and some n. If we start with 0 cells, we're going to end with 0 cells. And if we start with n cells, we're going to stay with n cells. What happens in between? Well, we start growing exponentially, but then we get capped off. Let's go back to the slides. And here we are. So, yeah, like we said before, this one term gives us that exponential growth. And like I said before, the growth will slow as x approaches n. It's kind of being limited in some way. When we do this full solution that you can see on the board behind, we get this quite complicated looking term where x0 is again the initial condition. And when we plot it with these parameters, we get what we said before. See how n is equal to 0 here, and it's being cut off. It's like the maximum number of species is 100 there. And now let's go back to our model from before, where we talked about cell growing in a dish, say. Here we are. You can imagine, like, if you grow cells in like a petri dish, they're going to be limited after some point by what we call carrying capacity, the maximum number that you can even fit into a dish. And that's maybe an improved model. So it's tempting to think that the exponential model was rubbish, and this is now the good model. But maybe there's new ways to improve this model. We're going to talk about some competition models now. So before there was just one species that we were talking about. Now let's introduce two. So here we've included a kind of a case study into grey squirrels versus red squirrels. So in the UK, there's kind of a famous case where there's two competing populations, but the grey squirrels have largely run out. They've largely won out. There's much more grey squirrel population than red squirrel in the UK. And they've had a go at modelling some of these. So let's have a look here at these equations. So here, R is representing like the number of red squirrels. G here is the number of grey squirrels. And what do these equations show? So these first terms, we've said there's some logistic growth here, where hopefully you recognize these terms looking similar to the ones before, where these populations will start to grow over time, and then they'll flatten out. And once they reach some maximum carrying capacity here. But then what are these added terms? So these here are death due to competition. So here A and B are just some parameters that we've got. And we're timesing these together. So this can be quite tricky to think about. What is the rationale of multiplying R and G here to give us this some competition term. This is quite common in models of this type. Why would this give a good competition term? Well, think about it. You can think that if there's a large amount of red squirrels and grey squirrels, then there's going to be a high amount of competition. This means that there's going to be this term here is going to cause a large negative be added to the red squirrel and the grey squirrel population. And that said, if one of the population is very small, if there's 0 grey squirrels, then this whole term is 0. Similarly for red, if there's 0 red squirrels, then there can be no competition for red squirrels or grey squirrels. Let's have a look at some of these dynamics. So if we set our initial conditions to be 0.1, this represents like 10% of like our population, say. You can get a model that looks like this, where defining these A and B parameters, we've forced here the red squirrels to tend to the full population and the grey squirrels to die out. Now, you might notice that these equations look very similar, and you could relabel them and they'd look exactly the same, say. So using that, if we changed the values of A and B, so now A was equal to 2 and B was equal to 1.5, what do we think this is going to look like? Again, assuming that they start with the same amount. Yeah, exactly, correct. Yeah. So what we said in the chat, the graph flips, and that's exactly what we're seeing. So you change the numbers and the exact same shape of plot is produced where now the grey squirrels win out. And we might argue in the UK, say that this here that we're looking at now is maybe a more suitable model where the grey squirrels have won over the red squirrels. But that isn't the only model that we can get. We can also get cases where they're bistable, meaning that you have 2 populations which maintain equilibrium, which for the vast majority of species on the planet, this is what we're getting, at least ones that are like currently alive in ecosystems, right? We're getting these stable states. And there's a lot of further maths that you can go into to have a look into this, called steady state analysis. So in the first 1 or 2 years maybe of an undergrad degree, you would definitely be looking into models like this, and you can provide some really nice insights into some fairly simple maths, analyzing these equations, and you can tell analytically whether or not you're going to get one species winning out or them both remaining stable together, or both dying out for that matter too. Let's look at some more. So let's consider the Lotka-Volterra equations. So these are slightly different. This time we're still talking about species in conflict here. This time S is representing some population of sheep and W is representing some population of wolves. So let's go through this like step by step in these equations. So like as we can see, if you ignore all the other terms, we're saying that the sheep is having this some exponential growth rate starting off relative to some rate alpha. Then you've got this competition term in the sheep here, like we saw before with rate beta. This is what you can think of as the death of the sheep due to the wolves. Since they're being multiplied, there's more wolves, this rate is higher. Going to the wolf equation, this term here is the reproduction of wolves, almost like the amount that's being fed into by sheep here. So looking at the death of sheep due to wolves and the reproduction of wolves, these terms are very similar. They're both S times W times some parameter. And you may think that that's a good model. You might think that's a bad model. Is that accurate? Should there be some natural birth of wolves that isn't being accounted for? Yeah, absolutely there is. But this is one of the points of this being creative equations, in that we aren't necessarily choosing something that's 100% correct. We're choosing some equations that fit a model, that work in the simplest way. Let's continue to this last step. And as you can see here, this last term here gives some kind of natural death of the wolves with relation to gamma. Now, the Lockwood-Volterra equations are quite famous in maths, at least in this modeling context, because they produce some very nice results of oscillating behaviors. Whereas before, we saw that our predator-prey models, like competition models, can lead to bistable systems where both like the gray squirrels and red squirrels could live in equilibrium. Here, it's a type of equilibrium, but it's not constant, in that first you see the sheep's peak, and then the wolves peak later, then the sheep die, and then the wolves die, and the sheep peak, and so on. And this kind of makes sense if you just think about kind of the internal logic of this. You think that sheep are growing, the wolves are kind of starting to increase, they're starting to have more food to eat. As the wolves eat more of the sheep then obviously die. Then there's no food for the wolves, so the wolves die, and so on and so on. And this, again, you can use what we were saying before about steady state analysis to try and look into whether or not this is a different stability than in the stable one, which they are. Now, yeah, as I said, it results in these oscillations of populations. We couldn't, like I was saying before, what happened to the natural birth of the wolves? What happened to the, you know, like the natural death of the sheep? Well, they weren't being taken into account for in the previous model. But we can make our equations as complicated as we want. You can play around with any of the terms and make it your own. So here we've started off with some logistic growth terms. I'm just playing around here. So here you've got the rate of the sheep growing is RS. They have some maximum population KS. Similarly, RW gives the rate at which the wolves reproduce, and KW gives the maximum population of wolves. Now these extra complicated terms, well, again, we can see the natural death of the wolves there as a nice one. And then here we've included the death of sheep due to the wolves, but in a more complicated way. This type of form is called a Hill function, which gives quite nice properties because they're limited between these parameters A and H. And then in comparison, we've got the reproduction of wolves, which flattens as the number of sheep increases. Maybe this flattening is due to, like, you know, wolves can't eat an unlimited amount of sheep in a day. They're limited by some kind of like hunting factor, or, you know, maybe they eat and get lazy, or who knows. These parameters are very flexible, right? And we can model these. Now, these are harder to produce results for analytically. You may not even be able to solve these using like pen and paper techniques. So these results have been done numerically, which means that you use a computer to basically solve them. And here we go. So we've plotted just an example of some trajectories, and here we're saying that the sheep, in this case, on these parameters that I've picked, die very quickly, almost like extremely sharply, actually, towards later times. It's almost like they're dying quicker and quicker and quicker until there's just none left. And this, of course, means the wolves have no food to eat, and they die out too. And there's like so many parameters here. There's obviously 1, 2, 3, 4, 5, 6, 7, 8 parameters here, which we can play around with and try to maybe fit it to some data that we've got, for example. And when you're modeling in a real industry, biological, even like a financial engineering context, the equations you use aren't set in stone. You've got a lot of variability to play with. So you need to start asking yourself, is it more useful to have the most complicated equation you can get your hands on, or is simple best? If we can describe a system using 1, 2 parameters, maybe we've got something that more people can understand, that can actually not be affected by noisy data. There's loads of different problems with these. Yeah, so as I was going on, which model is correct? On the right here, we're looking at some data which is quite famous for kind of showing a Lotka-Volterra type system with those oscillations, with hares and lynxes here from 1937, so quite old data. Should we use a more complicated model, or should we reduce it down? Oftentimes data we have isn't really exact. We might have the population of these animals every 6 months, every year, every 5 years. Maybe a very complicated model isn't suited to data that's that sparse. And this is, when you're modeling in the real world, this is very common. In fact, it's probably more common to have data that's not very good than data that's great. So something we need to highlight is the balance of simplicity and accuracy. How simple is our model, but it needs to also capture the behavior that's really going on. So we return back to that quote we started at the beginning, right? That all models are wrong, that some are useful. And oftentimes when we're trying to define models in the real world, we often follow this like kind of flowchart type behavior, where we get a real world problem, we try and define it, we use some kind of equations to use it, try and solve that, and see what the results are. And oftentimes the first go round, you're never going to get a model that's perfect. You're going to have to keep refining it over and over again, often against data, to see if these models are good and correct, or at least the best we can do. Useful models not only accurately describe data, but they allow us to make predictions about what's true. You might be able to think, well, I've got this model for how these sheep and wolves occur in populations. So what if all the sheep die out? What if there's a disease that kills 90% of the sheep? What's going to happen? And if you have a good model, then you should be able to test that. What if we have some population, 90% of the sheep disappear? What's going to happen to the wolves? And you can test to see, what if, are the wolves all going to die out? Are they going to return back to the states they were? This is the power of a good maths model. Yeah, and via those predictions, we can get insights onto what's really going on biologically, or in this case, yeah, biologically in our case, but physically, chemically, financially, economically. These are all tools that we use as modelers. So how has this been used in current research? So one of the problems that we're looking into in the group is in your microbiome. If you have, a system not with 2 species, but with hundreds, millions, more than millions of different species, how stable can these populations be? The equations that we use are very, very similar to the ones we looked at in this PowerPoint. Just you'll have more species to deal with. So if we have this like vast amounts of equations, can they stay stable? We know they kind of do in our gut, in a healthy gut, then we will have all of them living harmoniously. But then we can ask, okay, if we introduce like E. coli, a very like powerful, like fastly replicating bacteria, then how is this going to affect the stability of the whole ecosystem? And these are questions that are still in research, right? We haven't got great tools at the moment, so these are being developed at the moment using stuff like chaos theory, dynamical systems, which is the what we're looking at here, like the relationship of multiple systems of ODEs or other mathematical equations that are linked together, or we could think of these as random matrix theory, which you can look into as well. Moving on from here, so if you've been really inspired, which I hope you have been, to have a look, there's some very classical implications, like text that you can have a look at. So this book here that I'm highlighting, Mathematical Biology, is a key book. I'm sure you'll be able to find something online describing what goes on in Murray's book here. It starts to introduce what we're talking about, those like steady state behaviors, and goes on to talk about not only predator-prey models, but how you can get these like waves traveling in ecosystems. As you know, as cells grow over time, you might form this like wave of cells moving through a domain. I mean, you guys, as young people, you're definitely going to be on YouTube. And I think YouTube has such a wealth of good maths content. I mean, I'm sure I don't need to tell you about 3 Blue 1 Brown or Numberphile, but these videos here are some absolute key ones that can help you deal with some of these problems that we're looking at. So differential equations from 3 Blue 1 Brown. We've got an amazing series, but this video here just highlighting as a really, really strong contender there. And Numberphile's, the math of species conflicts, deals with a little bit of the kind of modeling that we've been doing here with predator-prey models.